Concentrated solar thermal, or CST, is a method of harnessing the thermal energy of solar radiation. The largest scale projects of this type are called power tower, where an array of mirrors, also known as heliostats, all focus sunlight to a receiver that reaches temperatures of over 550 degrees Celsius. So what this does is it heats up a working fluid, which in this example is water, that is used to produce electricity through a traditional steam turbine setup. So it's actually quite similar to a coal-fired power plant, except that the steam generating heat comes from the sun rather than burning a fuel. So what is the benefit of this technology? Well, first of all, it's a renewable and carbon-free electricity generating method. But what makes it different from photovoltaic or PV solar is that when PV produces electricity, it generates electrons directly. And so those electrons must be instantaneously used or stored in batteries. And battery technology is not really currently at scale. So with CST, the storage is actually built in, and this is accomplished by using a molten salt as the working fluid, and then a heat exchanger to produce the steam. So the molten salt can kind of be stored, as you can see in these two tanks, and then the energy can be released at a later time. So why molten salts? Well, molten salts have a high heat capacity. As we can see from this equation here, which is the form that we probably have seen in this class, the change in the energy stored is proportional to that heat capacity. And this equation is also, it's equivalent to essentially a formula that may be more familiar from chemistry, where the change in internal energy is equal to the mass times the specific heat capacity times the change in temperature. So what does this tell us? Well, the greater the heat capacity, the greater the amount of energy stored for a given temperature differential. So that's why we want to use these high heat capacity molten salts. And this ability to store energy means that electricity can be produced even when the sun isn't out by releasing that stored thermal energy. And this is particularly important during the evening when the electric load is still high, even though the sun is not shining. So that's why this technology is promising, because it solves that challenge of intermittency, at least to some degree. So, as you can probably see, there is a lot of heat transfer involved in this technology. So where we are going to be putting our main focus is on the reflecting and concentrating of that solar radiation using mirrors. So to do that, we actually have a real-life demonstration.
We're good. All right, so here we have a mirror that is similar to what you would see in a concentrated solar thermal installation, except this is just one single mirror. So the key thing about the mirror is that it has a parabolic shape. So essentially, no matter where the light is incident on the surface, it will be reflected to some focal point. So if it hits here, it'll go to the center, here to the center, right? So what that does is it takes the entire power or energy that is hitting this entire surface area and reflecting it to a very small surface area. So the heat transfer for that small area is much greater. So to demonstrate this, we are going to use this mirror to set some cardboard on fire.
This is the infrared thermometer. We're going to be using this to record the temperature at the surface of the cardboard that we're trying to set on fire. And we're going to be setting this to Fahrenheit. Alright, so here's another one of our attempts. So we burned in the box previously, but we weren't able to get a decent reading. So we're trying again. Right now, we're trying to focus the sunlight towards a specific focal point. The box is wobbling a bit, but you know, it is what it is. All right, if you'd like to focus on a specific point, I'll try to record. So I'm getting roughly 140 degrees Fahrenheit on that spot. Yeah, it's rather wobbly today. 241, 290, 218. So I'm reading 218. Yeah.
Smoking.
Okay. So it must be noted that the infrared thermometer that we're using isn't the most accurate. The way it works is it shoots a beam of collimated light in the form of a frustum. And what happens is the tail end of the frustum, the biggest section here, more or less tends to encompass a large range depending on how far you've got your infrared thermometer. We had ours quite far from the spot on the cardboard, so it does apply here. But what happens is that it takes a wide range of temperatures within the truncated end of the frustum, and it more or less takes the average as depicted here. So if you had different temperatures for, say, different spots, which are denoted by T1, T2, all the way up to Tn, what the infrared thermometer here does is it takes that average. But it's also denoted here as well for our viewing pleasure. And so the 260 degrees Celsius measurement that we got is rather close, but it's not necessarily the most accurate. Alright, so to try to calculate the diameter of the cardboard at which the light is being shown at, we're going to be using two equations. One will be the heat transfer from the mirror, which we can equate as Q is equal to AC, the absorptivity of the cardboard, which we can assume to be roughly 0.7, since cardboard retains heat well, and it's not a metallic material. AM, which is the surface area of the mirror, multiplied by PM, which is the reflectivity of the mirror, which we can assume to be 0.85 due to the fact that there are scratches and dust present, multiplied by G, which is the incident solar panel, or which is roughly 1,000 watts per meter squared, and multiplied by N, a mirror coefficient, which we'll get into later. For the second equation, we also want to calculate the emissive heat from the cardboard, which we can equate to be roughly epsilon, which is roughly the emissivity of the cardboard, or 0.81, multiplied by Stephen Boltzmann's constant, which is 5.67 times 10 to the negative 8 watts per meter squared, Kelvin to the fourth, multiplied by the surface temperature of the cardboard, not TS, it should be TC, which does happen to combust at roughly 477 Kelvin, and multiplied by the area of the cardboard being shown as. For the mirror coefficients, we're going to be assuming that the parabolic mirror acts as multiple mirrors. But to try to quantify that nature, we'll try to substitute N with a ratio between the surface area of the mirror and the surface area of the cardboard being shown at. So AM over AC. But we can simplify this further to be the diameter of the mirror squared over the diameter of the cardboard spot being shown at squared. Also for this, we're going to be assuming that the heat flux in regards to the heat being transmitted from the mirror and the heat absorbed by the cardboard to be equal, given that moment in time when the cardboard starts to combust. So in doing so, we will create heat flux by dividing the Q's by the surface areas of their respective equations. So in doing so, we divide the first equation by AM, or as mentioned, the surface area of the mirror. And for the second equation, we'll be dividing Q by the surface area of the cardboard being shown, which simplifies down to this. So since we're equating these, we could then simplify this further and isolate dc to try to get the value for that. We measured the diameter of the mirror to be roughly 0.889 meters. So given this, we've calculated the diameter of the cardboard being shown to be 0.445 meters. Well, this seems rather large, obviously. So we'll call this the incident combustible area. But also remember that this setup isn't really steady state, and there are a variety of factors that we haven't possibly accounted for when doing the simplification.
So DC represents how concentrated the radiation is on the surface. A larger calculated DC value than the experimental DC value is actually not surprising at all. The cardboard was not able to reach a steady state temperature before combustion began. So as shown in this figure here, a higher temperature would mean a lower DC value. So if there were no combustion, then the theoretical surface temperature would be able to reach a higher value, and then DC would go down. So the application of DC to concentrated solar thermal is that it's actually not necessary to make DC as small as possible as long as it's smaller than the receiver, right? Otherwise, some of the radiation would be going past it or outside of its range. More importantly, really, is the overall energy or area ratio, where we have the area of the entire array, which would be, if it consists of n mirrors, then the entire area would be n times the mirrors. So as you can see in this picture here, the more mirrors, the better. And a lot of mirrors can give a really high energy ratio, allowing really high temperatures to be reached. Also of note, in a CST setup, there would be no combustion. There would be no combustion and decomposition of the materials because they would be designed so that they would be able to operate at the high temperatures, and so a steady state could be reached. So hopefully through the demonstration of the power potential of just one mirror, which quickly set that cardboard aflame, we can kind of treat this as a proof of concept of sorts, where if we had a large number of mirrors, then we could get up to really high temperatures. Thanks for watching.